This is a definite integral. Also, this is an improper integral because the value of the integrand is infinity at x equal to 1. We have no any formula that can be used directly to evaluate this integral, but the method of substitution is also be inapplicable in this integral. So, we can use the series expansion of the function 1 over 1 minus x square for the evaluation of this integral. This is the only way to evaluate this integral. Now, we can write the integral. We can write again the integral is 0 to 1 this is equal to 0 to 1 natural logarithm x this is. Now we can use the series expansion of the function 1 over 1 minus x square. The series expansion is 0 to 1 natural logarithm 1 minus at first we can write this as 1 minus x square to the power minus 1 dx, and series expansion of this function is 1 plus x square plus x to the power 4 x to the power 6 dot dots this up to infinity. So, 0 to 1 this summation can be written in compact form, that is summation n equal to 0 to infinity x to the power 2n x to the power 2n dx. Now we can write this as summation n equal to 0 to infinity integration 0 to 1 natural logarithm x to the power 2n dx. This can be written as this. So, we can evaluate this integral by parts. We can evaluate this integral by method of integration by parts. So, this is equal to summation n equal to 0 to infinity integration by parts. First function is x to the power 2n, that is x to the power 2n. First function is natural logarithm x. Here we can use first function as natural logarithm x. Integration x to the power 2n dx minus integration derivative of natural logarithm x over dx integration x to the power 2n dx 0 to 1 and this is 0 to 1. This is the integration. So, this is equal to n equal to 0 to infinity natural logarithm x x to the power 2n plus 1 over 2n plus 1 0 to 1 minus integration 0 to 1 derivative of natural logarithm x is 1 over x and integration of this is x to the power 2n plus 1 over 2n plus 1 dx. This is equal to summation n equal to 0 to infinity natural logarithm one minus 1 multiplied by 1 to the power 2n plus 1 over minus, we can write as limit x tends to 0 natural logarithm x to the power 2n plus 1 over 2n plus 1. This is the lower limit. Lower limit can be written as limit x tends to 0 this, because if we put directly x equal to 0 in this function, the value of the function is undefined. So we can take the limiting value of this function at x equal to 0 minus this is equal to 0 to 1 x to the power 2n over 2n plus 1 dx. Now this part vanishes because natural logarithm 1 is 0. So this expression is summation n equal to 0 to infinity minus limit n tends to 0. We can write this as natural logarithm x over 2n plus 1 x to the power minus 2n minus 1, and this is also in the form infinity over infinity form. This is in the form infinity over infinity. So we can apply here L'Hospital rule for the evaluation of this limit. So this is this, and last part is minus 0 to 1 x to the power 2n over 2n plus 1 dx. Again we integrate this, and after integration we get x to the power 2n plus 1 over 2n plus 1 square. X to the power integration x to the power 2n is x to the power 2n plus 1 over 2n plus 1. So this is x to the power 2n plus 1 over 2n plus 1 whole square, and here limits are 0 and 2 1. 0 is lower limit, 1 is upper limit. So this is equal to summation n equal to 0 to infinity minus limit n tends to 0. This is in the form infinity over infinity, so we can apply L'Hospital rule to evaluate this limit, and also we can write this as this, and also we can apply the L'Hospital rule to evaluate this limit. So we can differentiate both numerator and denominator, and derivative of numerator, that is derivative of natural logarithm x, is 1 over x. Derivative of denominator is 2n plus 1 minus 2n minus 1 x to the power minus 2n minus 2, and value of this function at upper limit is 1 over 2n plus 1 square, and value of this function at lower limit, that is at x equal to 0, is 0. So only the value of this function is only minus 1 over 2n plus 1 square. This is, so we can write limit n tends summation n equal to 0 to infinity minus limit n tends to 0 x to the power 2n plus 1 over minus 2n plus 1 square minus 1 over 2n plus 1 square. This is, but value of this limit is 0, so this is equal to summation n equal to 0 to infinity. Only this value remains, this vanishes, because for limit n tends to 0, x tends to 0, sorry, this is not n tends to 0, this is x tends to 0, this is x tends to 0, all are x tends to 0 function. Function is this is a function of x, so the limit is x tends to 0, not n tends to 0. Here limit is considered as x tends to 0, x to the power 2n plus 1 over minus 2n plus 1 square, x tends to 0. These are x tends to 0, not n tends to 0. So, this value of this limit is 0 because x tends to 0, this is 0. So, 0 minus 1 over 2n whole square. This is equal to summation n equal to 0 to infinity minus 1 over 2n plus 1 square. This is, we can expand this summation, we get minus 1 plus 1 over 3 square, 1 over 5 square, 1 over 7 square, and so on. This is very well known series. This series is Fourier series, and also we know the value of this series. The value of this series is pi square over 8. Pi square over 8. Value of this Fourier series, this is well known Fourier series. The value of this Fourier series is minus pi square over 8. So, the value of this integral, that is 0 to 1 natural logarithm x over 1 minus x square dx is equal to minus pi square over 8, minus pi square over 8. This is the value of this improper integral, thus we have evaluated this integral.